This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark. The topic of the question is quantum mechanics. The question is, a quantum particle is subjected to the potential V as a function of x equals to infinity for x lesser equals to minus a by 2, equals to 0 for x greater than minus a by 2 but less than a by 2, and infinity for x greater than equals to a by 2. The ground state wave function of the particle is proportional to option A sin pi x by 2a, option B sin pi x by a, option C cos pi x by 2a, and the last option D cos pi x by a. Let us see how to solve this problem. The given potential profile according to the question is V as a function of x equals to infinity for x lesser equals to minus a by 2, equals to 0 for x greater than minus a by 2 but less than a by 2, and infinity x greater than equals to a by 2. The potential profile is shown by this schematic. Now we will consider the wave function for the particle in this given potential profile are psi 1x in the region 1, that is for x lesser equals to minus a by 2, psi 2 as a function of x in this region, that is x greater than minus a by 2 but less than a by 2, and in the third region the wave function is psi 3x, that is in the region x greater than equals to a by 2. Now the boundary conditions for this problem is given by psi 2 at x equals to minus a by 2 equals to psi 2 at x equals to a by 2 equals to 0. This is because in the first and third region the potential is infinity. So no particle wave function can exist in the infinite potential region. So psi 1x and psi 3x should be 0. Also at the boundary, these two wave function, that is psi 1 as a function of x and psi 3 as a function of x, should be 0. Now at the boundary also the wave function should be continuous. That is why the wave function psi 2 at the boundary, that is minus a by 2, and psi 2 at this boundary, that is at x equals to a by 2, should be 0. Now we will solve the one-dimensional Schrodinger equation in the region 2, that is in the region for x greater than minus a by 2 but less than a by 2, to get the particle wave function in this region. So the one-dimensional Schrodinger equation is given by minus h cut square by 2m times d square psi 2 as a function of x dx square plus v as a function of x times psi 2 as a function of x, where v as a function of x is the potential in that region, equals to E times psi 2 as a function of x, where E is the energy of the particle. Now in region 2 the potential is 0. So this equation can be written as d square psi 2 as a function of x dx square plus 2me by h cut square times psi 2x equals to 0. Now we will write this quantity 2me by h cut square as k square, where k is the wave vector for the particle wave function. So the equation can be written as d square psi 2x dx square plus k square psi 2x equals to 0, where k square equals to 2me by h cut square. Now for our case the energy of the particle is greater than 0, that is E greater than 0. It concludes that k square should be greater than 0. So k has the real value. For this kind of condition, the solution of the equation will be psi2 as a function of x equals to a times sine kx plus b times cos kx. Here a and b are the constants. Now we will apply the boundary conditions, that is psi2 at x equals to minus a by 2 equals to psi2 at x equals to a by 2 equals to 0. Now we found that our wave function in the region 2, that is psi2 as a function of x equals to a times sine kx plus b times cos kx. At x equals to minus a by 2, the psi2x is minus a sine k by 2 plus b cos k by 2, that is equal to 0. It is coming from this boundary condition. Also, psi2 at x equals to a by 2 equals to a times sine k by 2 plus b times cos k by 2 equals to 0. So we have these two equations now. First, we'll add up these two equations. So we'll get psi2 at x equals to minus a by 2 plus psi2 at x equals to a by 2 equals to 2b times cos k by 2 equals to 0. So we have cos k by 2 equals to 0. Now, any cosine function can be 0 for the values k by 2 equals to any odd multiple of pi by 2. So our k by 2 will be odd multiple of pi by 2. So that can be written as 2n plus 1 times pi by 2, where n takes the values 1, 2, 3 and so on. So integer values will be taken by n. We can write this as k by 2 equals to m pi by 2, where m equals to 2n plus 1. So the values for m will be odd integer values, that is 1, 3, 5 and so on. So we found that our k value will be m pi by a, where m equals to odd integers, that is 1, 3, 5 and so on. And at this condition, the a equals to 0 and b not equals to 0. So we can write the wave function psi2 as a function of x equals to b with a subscript m times cos m pi x by a, where m equals to odd integer values. Similarly, we will subtract those two equations, that is psi2 at x equals to a by 2 minus psi2 at x equals to minus a by 2 equals to 2a times sine k by 2 equals to 0. So from here we can write sine k by 2 equals to 0. That means k by 2 will be integer multiple of pi. So n will be 1, 2, 3 and so on. We can write this k as 2n times pi by a. Now we will write this 2n as m. So m will take the values 2, 4, 6 and so on. So the m values will be even integers. So we have k equals to m pi by a, where m takes the even integer values, that is 2, 4, 6 and so on. And for this condition, the a not equals to 0 but b equals to 0. So the particle wave function will be psi2 as a function of x equals to a with subscript m times sine m pi x by a for m equals to even integer values. So the complete solution for the particle wave function will be psi2 as a function of x equals to am times cos m pi x by a for m equals to odd integer values, and psi2 as a function of x will be bm times sine m pi x by a for m even integer values. Now for the ground state, m value will be 1, that is odd. The particle wave function at the ground state will be psi2 as a function of x equals to a1 times cos pi x by a. So the particle wave function will be proportional to cos pi x by a. Hence, the ground state wave function, that is for m equals to 1, of the particle is proportional to cos pi x by a. That is our option D. Now, we will see a different approach to solve this problem. We can solve this problem with the help of a known result. Let us consider this kind of potential profile. That is, the potential is infinite for x lesser equals to 0. The potential is 0 for x greater than 0 but x less than a, and the potential is infinite for x greater than equals to a. So this is a very well-known problem for a particle in a potential well having width a. For this problem, we know the solution will be psi1x and psi3x will be 0 in the infinite potential regime, and psi2x will be root over 2 by a times sine n pi x by a, where n takes the integer values, that is 1, 2, 3 and so on. So using this solution, we can get the solution for the given problem. Now we will shift the origin from x equals to 0 to x equals to a by 2 in the older well-known potential problem. So if we shift our origin from x equals to 0 to x equals to a by 2 in this potential profile, so our coordinate system will get transformed. So in the new coordinate system, the potential profile will look like this. So the potential barriers in the transform coordinate will be at x dash equals to minus a by 2 and at x dash equals to a by 2. So now we get the potential profile same as the given in the question. In the new coordinate system, after transformation, we can connect the older coordinate system to our new coordinate system, and that is given by x dash equals to x minus a by 2. So we can write x equals to x dash plus a by 2. So the particle wave function in the new coordinate system will be transformed from psi2 as a function of x, that is the older wave function in the well-known potential problem, to psi2 as a function of x dash in the new or transformed coordinate system. Now for the older problem, we know psi2 as a function of x is equal to root over 2 by a times sine n pi x by a. Now we have transformed our coordinate system from x to x dash. So psi2 as a function of x dash will be root over 2 by a times sine n pi by a times x dash plus a by 2, because x has transformed to x dash plus a by 2. That has been shown in the previous slide. So the wave function in the transfer coordinate system will be root over 2 by a times sine n pi by 2 plus n pi x dash by a. For ground state, that is for n equals to 1, we have psi2 x dash equals to root over 2 by a times sine pi by 2 plus pi x dash by a. So this will give us root over 2 by a times cos pi x dash by a. Hence, the ground state wave function of the particle is proportional to cos pi x by a. That is the option D given in the question. We solved this problem in two different ways. From both the solutions, we found that the answer for this question, that is the ground state wave function of the particle, is proportional to option D, that is cos pi x by a.